Good morning, everybody. This is going to be a relatively technical presentation where we're looking for advantages measured in the orders of magnitude. And it's with some embarrassment I have to say that your ability to understand me speaking English is orders of magnitude better than my Italian, so my apologies for that. So I work in the CTO's office of ANSYS. The CTO's office is responsible for setting the technical path for many of our products. I'm showing you a video of where I started my engagement with ANSYS, which was, I've been working as an engineer for 35 years now, and for all but 33 of those, I've never actually worked for ANSYS until they acquired the company that I worked for last. But for 33 of those 5 years, this is LS Dyna that I used back in the 90s, working for the UK Ministry of Defence. I then spent 2 years doing something else, and ever since then, I've either been using technology that has been acquired by ANSYS or worked in organisations that have been acquired by ANSYS, and now I work in the CTO's office in ANSYS. And this is the sort of technology, the solver technology that ANSYS is rightly renowned, very well renowned for. And all of the other presentations that are following me today are going to dwell on the excellence of this solver technology. I'm not going to talk about solver technology at all. What I'm going to talk about are the advantages that we see from delivering answers to the questions that you and our customers ask in the fastest time possible. What that means is that we have to make sure that we're answering the question with the right degree of fidelity at the right time. When we're doing trade studies, we shouldn't be looking to provide high fidelity solutions. When we want high fidelity solutions in terms of very highly accurate solver solutions, we should be looking to do that as few times as possible, because high fidelity solutions take a long time. Now, I was acquired into ANSYS as having spent $5 billion over the last 20 years or so acquiring technologies. ANSYS is a very heterogeneous organisation, made from homogeneous parts, as it were. But if you look at this acquisition strategy, 20 years ago they were focused, or ANSYS was focused on acquiring more solver technology, so Fluent and so on, Medini, Optis, Granta. Now, ANSYS, the acquisition projection is more towards digital engineering. What that means is we're not just focused on the high fidelity solver technology that we're rightly famous for. We're trying to make sure that we can pose the question in order to deliver answers faster. What does that mean for technology? Within ANSYS and the CTO's office, we have 5 major technology pillars that support the technology roadmap that the CTO's office owns. Obviously, our core solvers, we focus a lot of our efforts making sure that we are addressing the solving of the partial differential equations that our technologies are based on as quickly as possible. So whether it be CFD, the Navier-Stokes equations, or the Euler equations for structural and thermal, or the Maxwell partial differential equations for low and high frequency electromagnetics, we spend a lot of effort making sure that we are solving the finite volume problems as quickly as possible, or the finite different problems, or the finite element problems that we are solving. That allows us to make sure that we adopt all sorts of methodologies to deliver more accurate meshing or more accurate geometry conversions and advanced analysis, and particularly multi-physics. I think the majority of the presentations later today all cover multi-physics, and it's the ability to deliver simple multi-physics solutions, which makes ANSYS very special. Having solved the partial differential equations as quickly as possible, we then want to make sure that we are taking advantages of high-performance computing. Allowing particularly CFD and the electromagnetic solvers and the explicit dynamic LS-Dyna to work better on fine-grained GPUs, to allow that parallelization of the solution of the partial differential equations, rather than taking a sequential approach, which you do with a CPU. There's lots of technology that we put within the GPU capabilities in order to, for shared memory assignments, so that a single problem can be discretized into a particular size, so that it can be solved on the memory of a single GPU. And this is where orders of magnitude accelerations can be found. Artificial intelligence is the third technology pillar within ANSYS, and there are products which rely on artificial intelligence. But also, artificial intelligence is key to making our software easier to use. I'm only going to give one example here, and that is the unified turbulence model, for example, within Fluent. I think there are over a dozen different turbulence kernels within the different CFD programs and solvers in ANSYS. Each of those kernels requires a different set of parameters to allow them to operate, and each of those parameters has a variety of influence on that solution. But by creating a meta model from literally thousands of CFD runs, we've created a unified turbulence model, so that the different kernel and the different parameter values for each of the appropriate kernels can be selected automatically during the run, so that the pressure drift differences, the mass balances, or the different geometrical features within the fluid flow, which influence the performance of the turbulence model, can be selected as appropriately. What that means is that we've removed the need to have 30 years of experience to run a turbulence modeling capability with ease. Cloud and platform, obviously, the accessibility of hardware now on the cloud is very important. And what we've seen is that cloud-based acquisition of GPU technologies particularly can itself lead to orders of magnitude difference in the solution time for the more complex solutions. And what that means is that by making our the whole technology stack cloud ready, it allows our customers to access hardware that they don't necessarily want to buy themselves relatively easily. And the final pillar is digital engineering. And rather than talk about it on this particular slide, digital engineering is going to be the entire focus of the rest of this presentation. Now, digital engineering is a key driver today, and it's mainly focused on delivering on 4 requirements that I think every one of our customers is looking for today. Technology is advancing rapidly. It's advancing more rapidly today than it has ever been in the past. And in order to take advantage of that technology, we need to get it into the market as quickly as possible. Our products, and the products that you are either manufacturing, designing, or operating, are becoming orders of magnitude more complex. And that requires a greater number of decisions to be made in a shorter amount of time. What that means is that the information needed to balance the judgment needed to make those decisions needs to be presented in an orderly fashion, so that those decisions can be made in an automated way and repeatable way. The time to market for all of these more complex solutions is now required to be dropping. GCAP is a perfect example. 50% reduction in cost, 50% reduction in delivery time. Again, an enormous undertaking, but we will be able to deliver it, I'm sure, with the use of the right sort of technology. Not just ANSYS technology, but technology across the board at every stage in the development, from the stakeholder requirements to operations. All of this needs to be delivered at a reduced cost. So, I'm going to give you an overview of some of the technology that ANSYS is building at the moment. And I'm going to use this representation of a product life cycle. This representation is a V. I don't want to get into a discussion about which model we should be using. It could be a V. I've seen W's recently where AI needs a training session in the middle. I've seen spirals and I've seen circles. It's just a model of the product life cycle. Let's not get into that in too much more detail. But I'm going to use this to highlight some of the technology outside of the solvers, which ANSYS is developing continuously in order to try and make sure that we deliver on that promise that I mentioned. The promise that we can deliver answers to the right level of detail as fast as possible so that our customers can finish their programs as quickly as possible. So the first one is the design reference mission. Design reference missions can be seen in the old style world as the stakeholder needs, instantiated into a library of actual missions which the system, when delivered, should be able to deliver. This allows us to avoid trying to use vocabulary or letters within the stakeholder needs community, and it also means that when we come to the validation stage, we can directly apply the physics of our system onto the stakeholder needs to demonstrate that the system can, in order to virtually validate the system directly. So design reference missions, or a library of design reference missions, can then be decomposed, most importantly, into a set of requirements, numerical requirements, that we can then use to drive the trade-off analysis and then the virtual verification of the system at every stage. The requirements are just one step in the model-based systems engineering modeling approach that we see in these more complex solutions that our customers are beginning to develop. Once we have the requirements ready, we can then identify the functions that the system will need in order to deliver against those requirements. And we can understand the structure of the system that is going to deliver that functionality. Also, don't forget, I think every space system, every defense system out there now, they're no longer physical assets, but cyber-physical assets. And so we also need to be able to instantiate the logical or the software performance of that product within the system. And as soon as we have the model-based systems approach, we have to recognize that these are not just physical systems, but they're physical systems with electronics hardware in them, with software running on that electronics hardware, and they have to deliver that capability. And because they have a software and a sensor architecture, it means that they are vulnerable to cyber attacks. So we have to immediately start to build the safety case and the cyber security processes in order to safeguard the logical performance and safeguard against attack from bad actors out there. We still haven't decided how we're going to deliver on the system stakeholder requirements at this point. So the next stage is to start building an understanding of, in this instance, the physical architecture which is going to deliver on a set of requirements. This is a video from a customer of ours, Northrop Grumman, where we are far from high fidelity finite element analysis, but we are using a very coarse meshed finite element model here to run through a design of experiments that understands how we can maximize the takeoff weight and maximize the range for different mass properties, different inlet designs for the engine, different power plant parameters depending on how many compressor stages they've got or how many turbine stages they have. The shape of the airframe, the wing angle and the length of the wings, and then the life cycle cost models to make sure that we're optimizing not only performance but cost. And for all of that, we then want to compare the air behavioural envelope to demonstrate that it can deliver on the mission that we are building this system to deliver upon. So we can start making the best decisions early on, because without making those decisions early on, again, if we're delivering a satellite system, we want to be able to make sure that we are delivering the sensor, the comms capability, and the battery power supply, and the solar panels. Without those, we could easily... What's the difference? We could easily get confused and not... We can lose track of the stakeholder needs so that we're not delivering them towards the end. What that means is that we actually optimize the solution architecture at this point. If we decide that we should be using a different propulsion system of our satellite in space, that decision is going to be extremely costly, both in terms of time and money. So now, solvers. I mentioned solvers a lot in this presentation, and I said that I wasn't going to mention solvers, but for the rest of the presentations today, we've got at least 2 CFD presentations, so fluid dynamics in the second column from the left here, using 2 different methodologies, one high density fluids and one low density fluids. Giuseppe, who is going to be following me later today, is going to be talking about hypersonics. We've got a presentation on electro-optics, and I think Matteo is going to mention the stop analysis. So that's a multi-physics structural thermal optical analysis. And then we've got a couple of antenna coupling presentations for electromagnetics, and then on the left-hand side here we've got some thermal structural interaction presentations. So a lot of today's presentation will be on the solver mechanics, or the solver physics, and my presentation here today is to demonstrate how, with digital engineering, you can significantly reduce the design cycle by asking the better questions earlier on in the design cycle and getting the answer that you need faster. So now we're at the bottom of the design V that we saw at the beginning, and we want to make sure that we are not impacted by the volume of detail that we can create with these models. So what we do at that point is to make sure that we can extract the essence of the performance of the models that we've been analysing and express them with reduced detail in the form of a reduced order model or a meta model. And then this includes not only the structural performance of the systems that we're analysing, but also the software performance. So, for example, we can build co-simulation examples where we're looking for attitude determination and control systems to make sure that we are controlling the entire orientation system within a satellite. So, for instance, for example here, if the satellite system that we're looking at is expected and being programmed to photograph part of Rome, perhaps it's trying to photograph the chimney on top of the Sistine Chapel to give 5 minutes head start on whether we have a new pope or not. We can see that we can identify where we want to orientate the sensor, and then the software controls the orientation system in order to point the sensor at the right spot. We can then take the data that the sensor is providing, reorientate the satellite so that the comms bundle is pointing at the base station, communicate directly to a single point on the Earth, and then reorientate the platform in order to replenish the batteries, for example, by providing the solar cells with the greatest impact to light. So the ability to remove the detail but yet exercise the entire systems models within the capability is really, really important. And there are more ways that we can do this. So this is a view of understanding how we can build an image of the environment that these assets are operating in. We can cope with understanding the global terrain and the surface clutter on the surface. We can understand how the troposphere is going to behave. We can understand how the ionosphere is going to behave. We can understand how the solar winds and solar weather is going to affect us, and the assets that we're putting into orbit. And then from there, we can use that and put that into an environment so that we can virtually simulate either single pieces of hardware, multiple pieces of hardware in a design approach, or make sure that we are developing a really good understanding of how the system as a whole is working. That's the one on the left-hand side. The one on the right-hand side here is a mechanism from our business unit in the States, the AGI, to create meta models based on data created by the solvers to educate the sensors and the logic which is assessing the data stream from the sensor to understand how different assets viewed, or sorry, the same asset, the same target, viewed from different orientations would look, and to use AI/ML to educate those sensors and the data stream to make recognizing those different assets much more straightforward, much faster, and therefore more efficient. And there's a very good, it's called Project Loch Ness, and there's a lot of detail on the ANSYS website about that, specifically for educating sensors and interpreting the data stream that come from sensors. So once there, what we need to do is understand the system that we have designed, how is that going to behave in operations? So all of the work that we've done on this satellite, this demonstration satellite that we're building, how is that satellite either going to work as a node in a constellation, or how are we going to model the constellation of assets as a whole? So for example, we might need orbit propagation to understand and accurately predict the satellite positions today and in the future by modelling the really complex array of forces observed on assets and satellites in space. Optimal orbit determination, for example, raw sensor data, we want to be able to turn that into precise knowledge of where the satellite or the satellites are and where are they going to be at any point in the future. Maneuver planning, this is also absolutely critical. We want to design and schedule satellite maneuvers for collision avoidance or orbit maintenance, but we want to do that using as little of the fuel on board as possible so that we extend the life of that asset to its maximum. There are always payload operations that need to be performed. This is to operate and manage the satellite payloads to maximise the mission output and support the real-time needs of those payloads. We also need to make sure that the real-time telemetry that's coming from the assets and satellites, we want to make sure that we're receiving it and monitoring it and making sure that we are curating the signals that are coming there so that we get the best from that real-time telemetry. Conjunction screening, I do like that. That to me is a euphemism. Collision avoidance is what I should really call it. We want to make sure that we really understand how our assets are operating and moving in space aligned with other objects, and particularly junk, in order to assess the risk. And then mission scheduling, to optimize the limited operational resources like ground stations to meet mission-based timelines and priorities. And I think the summary on the bottom right-hand corner here is the end-to-end space situational awareness. This is basically what we're trying to deliver. What is going to happen? When is it going to happen? And how long are we going to have in order to react to that situation? If we can provide that information to the teams who are managing the satellites and the assets of our constellations, then we can maximize and extend the life of those assets to their maximum, and then therefore get the best performance from them and get the best value for money. So that was a very fast journey through the design cycle and the operational life cycle of the asset and the sorts of technologies that we see ANSYS providing to us. Now, I spoke about the structural performance of our asset or the satellite system, or it could be an aerospace system or a ground-based asset. So there's the structural performance, the thermal performance, then we have the electronics hardware performance, we have the software performance, we have the safety analysis, and we have the cyber security worries. A lot of those designs and those aspects of the performance of the system are done by isolated different teams. The thermal team often has very limited contact with the electronic hardware team, for example, or the sensor teams. Multi-physics allows one team to often sidestep the requirements of others. What we see here is that all of those siloed teams can start to operate uniformly and together, so that in the same way that software is delivered, we can start to build an architecture of federated authoritative sources of the truth, so that we can build a working systems model at any time necessary within the design cycle. So, for example, we build the digital reference mission, or the library of digital reference missions to instantiate the stakeholder needs for our system. From there, we can, within the multidisciplinary analysis and optimization, we can use that to connect the requirements, store the requirements, and then start to build the trade-off studies. Then at the more detailed level, we can use multi-physics to verify the performance against the requirements stored in the model-based systems engineering model, and build digital twins or build ROMs, so that we can build systems models from the different components in the system, so that we can run them against the requirements. We obviously need to build the structure from materials, and we need the logical performance to be created from software. And then we can store all of the ANSYS efforts and other efforts in a simulation and process data management envelope that allows us to build those systems models very easily. And then we have to be aware that ANSYS provides some terrific technology, but none of our customers only buy from ANSYS. Not only do they buy simulation technology from other organizations, or they build it in-house, they also have PLM systems that we don't have, the ERP systems, so enterprise resource planning systems, application lifecycle management systems, in-house tools. Every one of our customers has their own sort of secret sauce embedded in their own in-house tools, and IoT systems. So we're very conscious that our customers do not only buy from ANSYS. What that means is that we create an open, interoperable and collaborative platform, so that we can provide the input into other systems, or we can take output from other systems in a very open and standardized approach. We do that because our main focus is to deliver the best results at the fidelity that our customers want in the least time required. And so with that, just some concluding comments. Designing today's systems, whether it be space systems or land-based systems or aerospace systems, the technology is changing far more rapidly than we've ever seen before. Our customers, you, want us to deliver that new technology into your systems as fast as possible, into more complex systems at a reduced cost. And so we will do everything to deliver on that. And with that, I just want to highlight a couple of white papers that are available out there. So the Digital Mission Engineering white paper, There's also a white paper on digital engineering, so a perspective on the adoption of digital engineering. So that's a white paper. It's quite thorough. I was happy to be involved in that last year or the year before last. It's quite a tome, but it does give a very, very independent introduction to digital engineering. And then there's an e-book, so Getting Strategic with Digital Engineering. That came out on Friday last week, and it's available for download. All of these are available at the Resource Centre on our website. So with that, thank you very much indeed for your attention today.
Ci sono domande, curiosità? Al termine di ogni intervento, di ogni presentazione ci sarà modo di fare domande, quindi sentitevi liberi senza una preclusione. Va bene.